I think we have a break.
Welcome everyone to the last talk of the day and also of the workshop. Thanks to all of you who remain with us till the very end of this. So the last talk of today will be delivered by Andrea Bertozzi. She is a distinguished professor of mathematics and of mechanical and aerospace engineering at UCLA. She's an expert in nonlinear PDEs and fluid dynamics, and she's also Betsy Woodknapp Chair for Innovation and Creativity. Before that, Andrea got her master's and bachelor at Princeton and also her PhD in 1991 at Princeton. And before joining UCLA in 2003, she was professor of mathematics and physics at Duke University. Andrea won a lot of prizes over the years. I'll just mention a few. The Sloan Research Fellowship in 1995, the Siams Kowalewski Prize in 2009, the Simons Math Plus X Investigator Award in 2017, jointly with the Nanosystem Institute, and very recently the Siams Feynman Prize in 2019 for bridging the gap between high-level mathematics and engineering. And this is just to mention a very minor portion of our achievement in the last years. So without further ado, I welcome Andrea, and the floor is yours.
Thank you. Can you all hear me?
Yes.
Okay, excellent. Okay, so good afternoon to everyone in the UK. Good morning to those of you who might be like me on the West Coast of the United States. It's a pleasure to be here with you this morning. And I'm going to speak about a body of work that has been ongoing in my group for about 10 years. Yesterday in the panel, one of the things we were asked was to describe, sort of a most inspirational area of our research, or sort of the style of research that we enjoy. And what I talked about was taking ideas from one area of science or mathematics and then bringing those into a completely different area. And so that's one of the things that I'd like to speak about today. That's a recurring theme in my talk today. And so without further ado, let me just begin by mentioning that this work would not have been possible without contributions from quite a number of students and postdocs. Since this is a special conference for women, I'd like to point out that there have been quite a lot of women involved in this research. Tiana Kostic, Christina Garcia Cardona, Hui Hu, Ekaterina Merkuriev, Xiaoyi Meng, and I think those are all the women on this slide, but it's on the order of half of the young people were actually female, and that was not by design. It sort of happened organically, right? These were, some of them were women in my departments. One of them, Christina, was studying nearby and decided to join our project from a nearby university. And I think it's really remarkable to have an area like this in data science that has, which is largely, in my opinion, a male-dominated field, to have so many contributions from young women scientists. Okay, so I'd like to start by presenting a little bit of the inspiration. So I'm going to do a little bit of review of some of the mathematics that goes along with low-dimensional geometric image segmentation, and we're going to see how that can be sort of translated into looking at high-dimensional discrete data sets. Okay, so this is an example from image processing online. It's sort of a recap of work that was done over the past 30 years in image segmentation using variational methods. And this is an image of Pascal. Pascal Getterer was a student at UCLA who wrote this paper. And he introduces several different methods for image segmentation. One is the classical Mumford-Shah method, and the other is the Chan-Vessey method. Vessey is my colleague Luminita Vessey at UCLA. And Tony Chan was also at UCLA when I first came almost 20 years ago. And so I was very familiar with their work. The paper, the Chan-Vesse paper, was published and won a prize in 2001, and I arrived in 2003. Now, let me just describe kind of in words what's sort of special about these models. The models are trying to find a boundary between two different or many different parts of an image for segmentation, and that boundary takes the form of a curve, which is denoted by gamma in these functionals. And so the idea is that you want to minimize this energy by choosing an appropriate, in the case of Mumford-Shaw, piecewise smooth function u, which is smooth away from this curve gamma, or you want to choose a piecewise constant approximation. Hold on, I need to switch mice here. Okay, so you want to choose a piecewise constant approximation where you have constants C1 and C2, so that your image, which is F here, is as close as possible in a least squared sense to the constant C1 or C2 on either side of this curve gamma. Now, what's interesting about these two models, so Mumford-Shaw, by the way, is a generalization of Chan-Vesse. So in the Mumford-Shaw case, you have a least squares fit to the piecewise smooth function. And then this term here basically enforces the smoothness. So this is the L2 norm of the gradient away from the boundary gamma. But both of these models, right, the Chan-Vesse model is the special case of Mumford-Shaw, if you will, where you have piecewise constant instead of piecewise smooth. So this term disappears, and this term becomes these two constant terms. But both of these models have a special geometric term, which is sort of innocuously hidden at the end of the functional, but it's very important. And that is the length of the boundary gamma. So that's what this notation means. The straight bars means that we're just measuring a geometric quantity, the length of this curve, times some parameter. That's a fixed constant parameter nu. And these are models in image processing that bring geometry into the equation. So now I'd like to go over a little bit of the mathematics related to this seemingly innocuous geometric term. Notice that, like for example, in Chan-Vesse, these two terms are very, very simple, right? They're just a least squares fit. So this term, although it seems innocuous because it's written with very simple notation, actually has sort of all the interesting complicated math. So let's go on to this next slide where we look at how to look at the length of the boundary in terms of the total variation. Okay, so how do we do that? So imagine that you have some region omega and it has a boundary gamma, and maybe you have objects that you're trying to segment in the image. And we'd like to represent the length of the boundary using information about a function that defines this region omega. So let's let u be the characteristic function of omega. So it's 1 inside and 0 outside, or something like that. It has a jump discontinuity across this curve gamma, where the boundary of omega is gamma. We can actually, my slides are misbehaving. We can actually write the length of the boundary in terms of the L1 norm of the gradient of u if we view this in a weak sense. And that is the definition of the total variation. So the total variation of the characteristic function, so that's a function in the whole plane, actually allows us to measure a geometric quantity, which is the perimeter of the support of that function. And another interesting piece of mathematics that I won't go into detail on because that would be a different talk is how one can relate this L1 quantity here, right? So for people who are familiar with L1 compressed sensing, this idea of total variation is certainly studied in that context, but it actually has a whole nother life. And so I want to talk about that life, which is this geometric context. And one way you can approximate this is using what are called diffuse interface models, and that brings in something called the Ginzburg-Landau energy. So the Ginzburg-Landau energy is an energy that replaces this L1 term here with an L2 term. So those of you who are familiar with the functional analysis will recognize that changing a 1 in this exponent here to a 2 is a big deal. Because when you have a 1 here, you can permit functions with jump discontinuities, as we have in this case here. But if you have a 2 here, you cannot, right? If you have a 2 here, that enforces some smoothness. It imparts some smoothness on you. A bound in this L2 norm of the gradient imparts some smoothness to you. And we can no longer have jump discontinuities across a curve like that. But there's a small parameter epsilon. So that means that when you have the small parameter, that introduces what we call a diffuse interface. So there's still an interface present, it's just that it's smoothed over some length scale epsilon. And then to enforce the binary, the almost binary nature of U, we also include a term that has a very strong constant in front of it, 1 over epsilon, and it's a double well potential. So this double well potential tries to push U into one of 2 values. So it has a shape of like a double well, and at the 2 minima, you're going to find the values that would be essentially the characteristic function values in this case here. Okay, so that's your Ginzburg-Landau energy. And actually there's a theorem that was derived several decades ago that tells us that in a sense of gamma convergence, this Ginzburg-Landau energy converges to the total variation semi-norm. So they are, rigorously mathematically related to each other in the epsilon to 0 limit. And one can use this fact because in terms of variational calculus, before we had all the beautiful tools, from compressed sensing to try to minimize something like this. Back, when I got into image processing, back in, this would have been like around the year 2000, the standard method, the state of the art for minimizing total variation in 2 dimensions was to solve a partial differential equation. One actually would, for example, just do a gradient descent PDE. So you get a nonlinear partial differential equation for U. It's very nonlinear, it's singular. And it was somewhat expensive to solve. So there was sort of an industry out there, a small industry, but I contributed to it, as did a number of others, where one can replace total variation by this functional here. And notice that if we take the first variation of this functional, because it's purely quadratic, you get the Laplace operator, and we have very, very fast codes for solving things like the heat equation with a Laplace operator. So that was kind of a piece of work that happened in image processing, like on the order of 20 years ago. Okay, but there are some other beautiful geometric ideas, right? So if you take the Ginzburg-Landau functional and you compute the first variation of the entire functional, not just the quadratic part, but the double well part as well. The double well has no derivatives in it, right? It's just evaluated pointwise. So the first variation also is evaluated pointwise on U, and it has a very simple form. It's, you can use just basic calculus, right? So you get the gradient descent, the descent part gives you a minus sign, and then this is just the derivative, the ordinary derivative, right, of W with respect to U. And so you get a nonlinear partial differential equation for U, where the first term, so this is just the time derivative of U. The evolution of U is dictated by the Laplace operator on the right-hand side. So that would give you a heat equation, which is well known in physics going back a couple centuries. But then there's this additional double well term, which is pushing the values of U into one of the 2 wells. Basically, it picks whatever well is closest, and it's going to push it into that well. However, there is this parameter epsilon, and as epsilon gets very small, what actually happens with the dynamics of this equation is that you have an interface between the 2 values of that double well, and that interface moves, and it moves with a law that is very close to motion by mean curvature. One can prove that in the epsilon to 0 limit, you recover motion by mean curvature. So that's some beautiful, geometry that goes back several decades in the pure mathematics literature. All right, so Now, going back about 30 years, there's this beautiful work by Marion and Benson Osher, and they said, hey, let's try to leverage this idea of these diffuse interface models. And let's notice that you have a fast dynamics and a slow dynamics, right? So you have an epsilon here and a 1/epsilon here, which means that this is slow compared to this, if you're thinking about it as a dynamical process. And so when you have this sort of separation of time scales, what it allows you to do is, for example, with the fast dynamics, what you can do is just push yourself immediately into the equilibria for that dynamics and then run your slow dynamics. And so they proposed something called the MBO scheme, which basically did exactly that. So they said, let's just solve the heat equation, the linear heat equation for a short time. And that we have lots of good techniques to do. For example, a simple one would be a pseudospectral method, right? So there's sort of an underlying pseudospectral idea I wanted to mention here, right? So you basically project everything onto the spectral modes of the Laplacian. And so we know just from basic mathematics that the eigenfunctions of a Laplace operator in all of space or on a periodic box, for example, are sines and cosines, right? So we can write those down explicitly. Those are Fourier modes. And then you have this beautiful tool called the fast Fourier transform, which allows you to go back and forth very quickly in a computational setting. And that idea is the basis for a whole class of numerical methods called pseudospectral methods. Okay, so that's the first part. That's the slow dynamics. The fast dynamics is flow into one of the two wells, but we actually know, like, just a priori what that equilibrium is, and it's just you pick whichever well you're closest to. So that's effectively just a threshold. So basically they proposed to this method where you solve the heat equation for a short time and then you threshold your data to get a characteristic function. And then you just repeat that. And if you do that, you can start with a characteristic function that has a perimeter like this C1. And then after doing that iteration, you end up with a new curve. But you don't get the same curve back because that heat equation step alters the location of that boundary. You get a new curve. And if you just follow these curves, if you're taking appropriately small time steps with the heat equation, you actually end up with dynamics, which is effectively motion by mean curvature. Actually, the time steps have to be in some range. So that's a little bit of a detail that I'm not going to go into. But basically, it allows you to solve a nonlinear geometric motion for a curve using basically just a heat solver in all of space. So that's the idea from MBO. And so these ideas turn out to be incredibly useful for looking at discrete data science problems. And so that's what I'm going to explain. So the idea is that we take all of these ideas from Euclidean space and geometric motion, the minimal surface problem, the Laplace operator, pseudospectral methods, the fast Fourier transform. We want to think about what are the analogs for these things and we're going to look at these data problems on graphs. So we're going to look at now at taking all of our data, pieces of data that have the same, the same size, right? So maybe they're all vectors of the same large dimension, and we organize them in something called a similarity graph, which I will explain. And the idea then to organize, once they're organized in a similarity graph, is we want to segment that information by solving a penalized graph minimum cut problem. So the graph min cut problem is something that goes from computer science that goes back quite a number of decades as well, but it's a completely different parallel line of research. It doesn't have any essential intersection with all of the geometric stuff that I've just described. But we also have this operator called the graph Laplacian, which has a lot of things in common with the differential Laplace operator, which lives in the continuum. The graph operator, the graph Laplacian, is just a matrix operator. It's discrete, but it has eigenvalues and eigenvectors, right? And so we can think about projections onto eigensubspaces of the graph Laplacian, just like we look at these pseudospectral methods in the continuum. The fast Fourier transform, there's no obvious analog over here. But we have other tools. So the other tools involve things like approximations of the graph Laplacian. Why would you even care about doing that? Because the Laplace operator for graphs is order n squared to calculate that thing. And with n pieces of data, you'd like to avoid n squared operations if you can, especially, scaling up to massively large data sets. So we have a couple other tools in our tool belt, and those are two different kinds of approximations of the graph Laplacian. One is called the Nystrom extension, which is a low rank approximation of the graph Laplacian. The other is our Rayleigh-Chebyshev methods, and those use sparse approximations of the graph Laplacian. So that would basically involve sparsifying your graph. And in each of those instances, we often only need a small percentage of spectral modes. And you might wonder, well, can you do the same thing on the left-hand side? And the answer is no. Typically, you have to use all of the Fourier modes up to the resolution of your grid, okay? Whereas, because it's finite dimensional, you're always making the problem finite dimensional on the left-hand side as well, but it's a different idea. And whereas on this side, there's a lot of redundancy built into the graph Laplacian eigenvectors, right? Because it's a similarity graph that takes n high dimensional vectors and then creates this Laplace operator, which is n squared. So because you're doing pairwise comparisons between vectors. So there's redundancy, and that redundancy kind of affords us this kind of a cheat, if you will, by allowing us to use in practice a small percentage of spectral modes. Okay, so let's kind of forge on here. So now I need to give you some details. So similarity graphs are weighted undirected graphs. So each node on the graph has a piece of data associated to it. And the edges of the graph have weights, and the weights are just values between 0 and 1. And they're often something like this, where x and y are the pieces of data on two nodes, and the weight connecting those nodes, w, x, y, would be something like this, the exponential of minus, sort of these radial basis function type ideas. So the exponential of minus the distance between x and y. And I haven't told you what that distance is, right? And then divided by some scaling parameter tau. And so the distance that you use depends a lot on the application and the context. You could use a simple L2 Euclidean distance, but you could also use something like cosine angle, which is what we do very frequently with things like hyperspectral vectors for hyperspectral imaging. You can also look at lots of different types of data. You don't have to restrict this problem to image analysis, right? You can look at things like voting records of the US Congress, vote vectors, right? And look at, how the Congress naturally segments into groups, which is very interesting. That's an exercise that a number of people have looked at in the past. There are papers written about that. You can also use it for more complicated image processing forms of data, such as the non-local means graph. The non-local means graph is created by taking patch neighborhoods of pixels rather than individual pixel values, and those are your high dimensional feature vectors, which become the nodes on the similarity graph. So these are some examples, and I'll show you some results from those examples. Now let's talk about cuts. So if I have a similarity, if I have any graph, it could be a social network or could be a similarity graph. One of the things that people like to do is solve graph cut problems. So that means that we want to somehow sort the nodes into groups, where we try to look at how much damage we do by cutting the edges between unlike nodes, right? So here's an example here, and the minimum cut basically is a problem where you try to minimize the sum of the edges, the weights of the edges between unlike nodes. And you can also do maximum cuts, but I'm going to focus on the minimum cut. And what's really cool mathematically is this minimum cut problem, which is famous in computer science. The minimum cut problem for graphs is identical to solving a total variation minimization problem. So that's beautiful, and that sort of opens a door for us mathematically. So what total variation problem are we solving? What we're doing is we're taking a function f and we're looking for it to be an assignment function for the groups, right? Which group do you belong to? So each of the nodes is f is evaluated on each of the nodes, and maybe it's 0 on the black nodes and 1 on the white nodes, for example. And then the total variation of f on the graph is just the sum over, it's the sum over ij of the weights wij times fi minus fj. So this is exactly the graph cut value, because if fi and fj are the same, then that's 0. This distance is 0 and you don't include that weight. But if they're different, then you include those weights. So by definition of the graph cut, this is the same thing. And so it turns the graph cut problem into minimizing an assignment function f, which takes on discrete values on the nodes from specific values. The weights are given and you try to minimize this sum. Okay, so that's interesting, and that opens a door for us to try to use some of all this lovely machinery from geometric PDEs, which seems a bit strange, but it turns out to be exactly the thing. So now I'm going to show you. So actually, very early in this work, I had a postdoc in my group, Yves van Gennep, who's now on the faculty at Delft in the Netherlands, and we have a paper from just, I guess, 9 years ago, where we showed that if you take the Ginzburg-Landau energy, this is a slightly different, is a sort of a variant of the one that I showed you on an earlier slide, but this is a graph version of Ginzburg-Landau. So you might say, well, how do you get Ginzburg-Landau on graphs? Well, basically the idea is that you replace the total you replace the L2 norm of the gradient, which is, in functional analysis, we sometimes call that the H1 semi-norm in the language of Sobolev spaces. Okay, but we're going to replace that with an analog in the graph setting, and that analog is called the Dirichlet energy. So that's this term right here. And it's an L2 norm where you include the weights in the sum. But it's differences of ui minus uj, right? So it kind of has the same structure to it as in a discrete setting that the H1 semi-norm does in the continuous setting. Okay, so we have that, and then we have the double well potential here, and we have a 1/epsilon term in front of the double well, and we just have a constant here, and there's some technical details as to why that is. This is our Ginzburg-Landau energy. This is just another notation for the Dirichlet energy here. And what you can prove is that this functional in a gamma, again, with a gamma convergence kind of sense, as epsilon goes to 0, you actually recover the total variation semi-norm of your assignment function. That's what you recover, and that is the graph cut metric right there. So that's interesting, because it says if we want to solve a penalized graph cut problem, we might be able to get away with replacing the total variation term with something like this. And why might we like to do that? Because the tricky part is going to be this, because we're going to have we're comparing ui and uj here. This is pointwise evaluated on the nodes of the graph, but this involves connections and weights. But this is a purely quadratic energy, which means that the first variation is going to be easy to write down. So it's very much in the spirit of what's been done, a couple decades ago in the image processing literature using diffuse interfaces. We want to do the same thing with the graphs. Okay, so looks like I'm missing some slides. Oh, I think my mouse is skipping around. Okay, good. I want to get to this slide. So this slide, let me just check the time here. Okay, good, I've got plenty of time. All right, so this slide has the graph. So I want to give you a little bit more details. So that Dirichlet energy, if we take the first variation, here it is written here. This is our Dirichlet energy, but you can just do a little bit of algebra and you can see that that's the same thing as, this is the graph Laplacian here. It's the same thing as u inner product, the inner product of u with the Laplacian of u. And the graph Laplacian is defined this way. Yeah, on the off diagonal elements of the matrix, we have minus the weights. minus the weights of the graph. And on the diagonal, we have the sum of the weights going into that node, right? Because the diagonal is picking out one of the nodes, right? So that's what it is. This is the sum of the weights going into the node, and these are on the off diagonals, we have minus the weights. So that's our graph Laplacian matrix, and we can write the Dirichlet energy, excuse me, in terms of this graph Laplacian. There also are some convenient rescalings of the graph Laplacian that can be used depending on the type of data set that you're interested in. And in a paper that I published with Arjuna Flenner in 2012, and it was republished with a little more follow-up work described in Scigest, right? In SciEm Review as a Scigest paper in 2016. If you're interested in looking at one of these papers, I recommend going to the later Scigest paper in 2016. And basically what we did was we took a leap of faith and we said, hey, let's try to write down a Ginzburg-Landau energy for the graph cut, and here it is right here. So this is the Dirichlet energy with the epsilon. This is our double well potential. So that's a quartic polynomial, and that's just a specific double well potential just written out and explicitly. And then we added, so now we're doing machine learning and we want to do semi-supervised learning. So we added another term, which is a least squares fit, to some training data. So semi-supervised learning means that you have a small amount of training data, a small fraction of your data for training, and that's the U0. And the lambda tells us when we have training data. So lambda would be 0 if there's no training data for that particular node on the graph. Most of the lambdas are 0, but a few of them will have non-zero values, and they'll show up in this sum here. So we proposed this before we had any theory, and we just said, let's try it. It worked incredibly well. And so that led us to proving this result with Yves van Gennep in 2012. And then, of course, once you see how well it works compared to the prior state of the art, we just sort of went to town with it. And the next obvious step was to try to use the MBO scheme rather than the full Ginzburg-Landau model. So the MBO scheme, that was a paper that was published the next year in SIMS, SciEm Journal of Imaging Science, with 2 of my students, Ekaterina Merkuriev and Tiana Kostic. Ekaterina is now on the faculty at Michigan State University, and Tiana is a scientist working for Microsoft in the Bay Area. So that's where they ended up. And what we did was we said, hey, let's use the ideas that were developed for MBO for image processing. And I do want to give a shout out here to Salim Esadoglu and Richard Tsai, who have a beautiful paper from 2006 showing how to do MBO, how to use the MBO scheme for image segmentation specifically, right? So a lot of what we did was somewhat inspired by their paper from 2006, only we're now in the graph setting rather than the continuum. And so basically what we're doing is we're evolving this evolution equation. It's now a coupled set of ODEs where Z is going to be your assignment function on the graph. This is the graph Laplacian. This is a form of the graph Laplacian. And this is the first variation of the least squares fit to the training data. So this is semi-supervised learning. So you're alternating between this penalized, I call this a graph heat equation because this is the graph Laplacian operator with a minus sign for the gradient descent. And it has a very similar role to the classical heat equation from PDE, right? And then we're adding a forcing term on here. And we're going to alternate between this graph heat equation with the forcing term and thresholding. So that's our MBO dynamics, right? You have effectively a linear operator here with some forcing, and then you have thresholding. And this is very fast, really, really fast. We have not found a faster method for solving penalized graph cut problems. So I have another paper with Ekaterina and some other colleagues where we compared the MBO scheme to some other well-known classical methods, right? So max flow is another well-known method from computer science. MBO is faster than it. Now, the one detail, of course, is that MBO is local, right? So you're doing the local energy descent. So it's possible that you could miss a global minimizer and only go to a local minimizer. So that's a catch that you have to be aware of. So if you're trying to solve a problem that's highly non-convex using MBO, you need to be a little careful. And we certainly have been aware of that in some of our work, but it is super fast. And so the algorithm basically looks like this. You create a graph from the data, but you don't actually calculate the entire graph because that's often prohibitive. So when I say create, that's kind of in quotes. You choose a weight function and then look at the symmetric graph Laplacian. Now, you don't actually calculate the whole symmetric graph Laplacian. You actually calculate eigenvectors and eigenvalues of the symmetric graph Laplacian. And what's really nice is that when we look at the energy minimization problem in this setting, that the only time you actually see the graph is right here. It's this linear graph Laplacian operator. You don't see it here, you don't see it here. So we can basically boil this complicated nonlinear optimization problem down to solving this linear problem here with some other nonlinear but very simple pieces. Okay, so that's the idea. And so if you don't know anything about nonlinear PDE, you still have, yeah, okay, let's get this set. If you don't know anything about nonlinear PDE, you still have the possibility of being able to do this kind of thing because you can boil it down to, basically finding the eigenvectors and eigenvalues and then just plugging them into a scheme. So that's basically what we do. You initialize U and then you iterate this two-step scheme that I described above. And then this red part of calculating a portion of the eigenvectors involves one of our favorite tricks, the Rayleigh-Chebyshev procedure and the Nystrom extension. Okay, and what's beautiful about this approach is that it scales essentially sublinearly with the number of classes. Like if you want to sort your data set into more than just 2, right? You want to sort them into 10 classes, like would be a thing you would do with the famous MNIST data set. It scales very, very well. And so this is basically a snapshot of the Ginzburg-Landau model for more than 2 classes, right? Instead of a double well potential, we have a multi-well potential. Here is our multi-well potential. K is the number of classes. We still have a least squares fit to training data. But what's beautiful is that all of the hard computation is basically bound up in this graph Laplacian term. And it is the same graph Laplacian, whether you're doing 2 classes or many, many classes. It's the exact same matrix. So that's what's beautiful. The assignment function becomes a vector instead of a scalar. And what we're trying to do here is to push the values of our vector assignment function U to the corners of the simplex in k-dimensional space. So these are the edges of your simplex, and it's perfectly symmetric with respect to all of the different corners of the simplex in k-dimensional space. So that's the method that we put together. And again, let me just reiterate that our assignment function becomes a vector. Okay, but it's typically a vector that's much, much lower dimensional than the total size of the data set, right? Because you would have a small number of classes compared to a large number of pieces of data. And this is work with Cristina Garcia Cardona and Ekaterina and Alon Perkis at CGU, and also Arjuna Flinner. Arjuna is now at GE Research. He was at China Lake working for the Navy when I was working with him. All right, so that's cool. You can also take these ideas and really write them all down in terms of numerical linear algebra. So, you can sort of take the PDE side of it out if you'd like to and just write it as a numerical linear algebra problem with a series of steps. So that's nice. And then, the results are nice. So for example, this is the MBO reduction for the MNIST data set using 3.6% of the digits as known. So a very small amount of training data, getting high classification rate, running in like a fraction of a second on a computer, really, really fast methods. And then, you know, the Nystrom is not something we did. This is older work going back to 2004. And basically what it does is it takes something like this is the weight matrix, for example, that basically does the pairwise comparisons of pieces of data. And it basically, like, so X would be a smaller set and Y would be a larger set. And if you think about a block matrix like this, you want to be able to approximate W without computing this big block here, W, Y, Y. And this is the Nystrom approximation right here. And so that's you know, in a nutshell, what we're doing with Nystrom. And just let me kind of show you what you get. So here's a data set that we worked with about 6 years ago. This is hyperspectral, long wave infrared image in the desert in Utah. And we were trying to identify a gas plume that's only visible in long wave infrared. And it's moving across a scene where you have foreground, a mountain, and some sky. And so you can take the Nystrom extension and you can take the hyperspectral pixels, right, as your pieces of your nodes, right, of the graph. And you can use the Nystrom extension to calculate, you know, maybe up to 100 eigenfunctions. And these are just 4 of them. And we're looking at, since they're eigenfunctions of the graph Laplacian, we're looking at them using false color, right? This is not real color, this is a false color image. But it's kind of picking out something that we might guess is the plume. And you might guess this is the sky. So we basically made some guesses, and Ekaterina thresholded the eigenfunctions to pick out specific pixels that we thought were highly likely to be in a certain class. And then a lot of pixels where we just didn't know. The white ones we don't know, and the colored ones we've assigned to a class. Then you initialize all the unknown pixels with random initialization, so it looks like salt and pepper noise. And then you just plug it into the MBO scheme. And after just a few iterations, you get these are different frames now of the video. And you have a beautiful classification with the sky, the mountain, the foreground, and here's the gas plume just moving across the scene. And it's semi-transparent, and you can look through it and see the sky and the mountain kind of peeking through the gas plume here in the middle. So we were really pleased with that result for this hyperspectral data set. I also want to say that there is a theoretical connection between the MBO scheme and graph total variation. So this is work done by, so this was inspired by work done by Salim Esadoglu and his collaborators, where basically what you can do is take your MBO scheme and show that it's actually minimizing in energy, right? So you can actually, it's not just an approximation, it has its own energy, right? So, so let's talk about that a little bit. So, right, so you can think about one iteration of your graph heat equation as having as you know, taking on the form of an operator. It's basically analogous to the diffusion operator over some time step of the Laplace operator. And so if you take that operator gamma tau, it's not the same thing as gamma convergence. It's also not the same thing as an interface gamma. So it's a diffusion operator. You apply it to your assignment function f, and then you take the inner product with f, and you look at that object. So basically what it is, if you think about it in Euclidean space, think about having a characteristic function, then letting it bleed a little bit, and then looking at the inner product with that characteristic function. What it does is it kind of picks up the bleed region, right? That's what it picks up. And if you calculate that inner product, it's kind of measuring as an approximation the length of the boundary, right? And that's so it does the same thing in the graphical setting. This bleeding operator, this diffuse operator, also conserves mass. And then, sorry, it's this quantity here. This quantity here actually approximates 1 minus f inner product with the bleed, with a scaling parameter approximates the graph total variation. And you can show that that's actually a functional that decreases as you iterate the MBO scheme. So that's kind of neat. And we did this in the specific context of unsupervised hyperspectral imaging. There's our gas plume again, and this is basically the Mumford-Shaw model or the Chan-Vessey model, which is unsupervised. So there's no training data in this case, and we're still picking up a very nice, well-defined gas plume. There's a little more noise between the mountain and the sky, but we're still getting quite a good segmentation result. And I think I don't have a lot of time, so I'm going to skip to. Yeah, I'll just mention this for hyperspectral. This works really well. So this is the well-known urban data set from hyperspectral imaging. It's a aerial hyperspectral image of a Walmart in Texas with a residential area nearby. And you can do quite well with this approach. This is ground truth, 4-class ground truth for the Walmart image. It's called the urban data set, which is well known in hyperspectral imaging. It's publicly available. You can take 10% of your data as training. You can do semi-supervised graph, semi-supervised or semi-supervised graph cut method using MBO, and you can see it's almost identical to the ground truth. But you can also do unsupervised as well using the Mumford-Shaw, piecewise constant Mumford-Shaw model, and it also does quite well. So it doesn't use the training data at all. And then, another unsupervised method using graph Laplacians that many people know is spectral clustering. And you can see the spectral clustering result is missing the Walmart building entirely, which is here, right? It's letting the parking lot be one class, parking lot and the building are one class. So anyway, that's just an example. I mentioned scaling, right? The scaling up to larger data sets, and also the fact that this model parallelizes very easily. So we have a paper from 2016 with Xiaoyi, where we show that this method, we have it running on a supercomputer at the Lawrence Berkeley National Lab. It's called Cori. It's one of their famous supercomputers that lives in like a sort of a warehouse size room. We're only using we're using one node on the supercomputer. So we're not using the entire supercomputer because the data set that we had just wasn't that big. It was 13 million pixels. So it was a graph with 13 million nodes. But it was still pretty big compared to some of the problems that we'd worked on before. And this is just showing that the runtime with our parallel code scales very nicely with the number of threads that we're using on that node. And we also have been able to really compress the runtime of the Nystrom portion of the calculation, which our original code was rather heavy on that. We were able to get that down to, to a much faster, more efficient way of doing that. So let's see. Yeah, I wanted to get on to one more topic here, which is a problem in network science, which is community detection. So that's basically another clustering problem. It's trying to find communities within a network. So networks are undirected graphs, right? They're typically nodes with adjacency matrices that are either 0 or 1. So you're either connected or you're not connected. But you can also have weighted graphs, and you can look at modularity optimization, which is a particular optimization problem to find communities. You can also look at that as a method for studying similarity graphs, right? It hasn't really been looked at so much when we got into this, but we discovered that this was very interesting for similarity graphs. So modularity, let me just tell you what it is. So you have to partition your network into subsets, and then you compute a score called the modularity. It measures the fraction of the total edge weight within a community minus the edge weight expected if the edges were placed randomly using some null model. So this comes from statistical physics. And in fact, the original famous modularity optimization paper was published in PhysRev-E due to Newman and Gervan. And so, yeah, so this is a well-known model. So what's interesting is the modularity problem It turns out you can write it as a penalized graph cut problem. And that's some of the work that we did, was to show that. And then once you can write it as a penalized graph cut problem, you can actually solve it with the MBO scheme. And for some problems, that's a really efficient way to solve modularity optimization. In fact, for machine learning, it turns out to be pretty good. So, so how do you show that? Well, the way you show it is you can, for example, you can take just the case of two classes. If you have a bipartition of a graph, then you can show that maximizing modularity is actually equivalent to minimizing this operator, this functional here, which is the graph cut where you have your subset, where you break your set into A and A complement. So that's your graph cut size, minus this penalty term, which is your resolution parameter gamma divided by the size of the set times the volume of the first part times the volume of the complement. So this is our penalized graph cut problem. And then of course, using total variation, we can rewrite this exactly as a total variation minimization problem on the graph. So let me just kind of go forward to the next slide. And what we show is that for two classes, like if you force it to have two classes, then the modularity optimization problem, that's a maximization problem, is equivalent to minimizing this functional here. And you can see graph TV is right here. And this is an L2 metric, but there's this term right here is a second moment term. And it does include some of the graph, it includes the weights show up here. So that's an important detail. But this actually generalizes to n classes like very easily, right? So this idea generalizes to any number of classes. So if you fix the number of classes, modularity optimization is equivalent to minimizing a penalized graph cut problem. And so once you know that, then suddenly you have a whole suite of new algorithms for solving modularity optimization. And so, for example, we can take the 2-moon data set, which most of you in machine learning know, and you can say, well, how many moons are there? Let's say we don't know anything about it. We just have the data. We don't know anything about it. We want to know how many moons are there. Well, you can compute the modularity score using the method that I described. We use the MBO method here, n-class MBO. And you can try different numbers of classes, right? And you get a modularity score for different numbers of classes. And we can see that the maximum modularity is for 2 classes. And this is the partition. And we say, oh, there are 2 moons, right? For 3-point clouds, we can do the same thing. The maximum modularity is for 3 classes, and this is the partition. So it found those just perfectly. So of course, you have to give it something more interesting like MNIST. And let's cut to the chase here. You give it MNIST, and we thought we would start with another code. We wanted to test the MNIST data set using what's called the Jen-Louvain code, which is a well-known code for modularity optimization. And so we took the MNIST data set and we used we used a particular graph for the MNIST data set that's fairly well studied in literature. And we just fed that graph, right? We just fed it to the Jen-Louvain code. And the Jen-Louvain code ran for, almost 11,000 seconds. So that's several hours. But what it comes out with is actually quite good. It says it actually gets 97% correct classification with 0 training data. So no training data whatsoever. You just give it the images from MNIST and you ask it how many different classes of images are there, and it says, oh, there's 11. So you might wonder, how can I get 97% correct and have 11 classes when there's only 10 classes? The answer is that the ones were separated into 2 classes. One was the one that was a straight stick and the other had a flag on it. And we count that as correct because it's just looking at the shape of the images. So Jen-Louvain, this code, although it takes forever, does completely, almost perfect unsupervised MNIST classification. So you might wonder, can we improve that? And the answer is absolutely, we can improve the time and we can improve the runtime by using the MBO method, right? So we can go to our method and we can improve the time here down to, you know, like a minute or two, right? We can get it down to a minute or two. Now there's a catch, which is that for MBO, you have to tell it how many classes. So in this particular calculation here, we tried different numbers of classes up to 20. And in this case, we just said, let's force it to have 10 classes and see what we get. But nevertheless, we see that there's a big win for certain kinds of data sets in using the MBO scheme for modularity optimization rather than one of the more classical methods. So it just depends on your data set. So this is an example. And so, you know, I've had several students work on this. So Zach Boyd is another student of mine who is now just starting a tenure track job at Brigham Young University, but he was my PhD student, and he also improved some of these modularity models for graphs and for machine learning problems. So he has a paper in the Journal of Nonlinear Science, for example, that looks at stochastic block models and describing these using ideas from surface tension, and then ultimately the MBO scheme to solve those problems or sort of related things. And I'm looking at the clock, so I'm almost at the end here of my time. So yeah, so it's kind of neat. You can actually think about models for, oh yeah, here we are. My slides are just showing up in weird order here. I don't know why. But yeah, so you can, so one of Zach's papers that was published a few years ago looks at a sort of convex, almost convex, but it's not exactly convex, but it has a more of a convex representation for modularity. He calls these the balanced, two versions of balanced total variation here. So these are equivalent. They're not approximations of modularity optimization. They're equivalent to modularity optimization, but again, for a fixed number of classes. And the method is even better than the work that Hui did a few years earlier. Hui, by the way, works for Google right now. So a lot of my students go into the tech industry, but a few of them are still in academia, and Ekaterina and Zach are two of those. Okay, so surface tension model, yeah, so this is kind of neat because there was some really nice work done not too long ago on like looking at problems with multiple surface energies in the continuum, and it turns out that you can take a lot of the mathematics from these you know, sort of crystal and surface problems and translate them into useful mathematics for solving these degree-corrected stochastic block model optimization problems. And then you can apply those to either network science problems or problems in machine learning. So that's some recent work that we did. This is work from Zach's thesis. And I'll just say that we've gotten, you know, some pretty good results using these models, both for, you know, some of these are, you know, sort of well-known, like Facebook and other like social networks, but you can also apply them to the plume data, which is definitely a machine learning problem. And, you know, this is a modified mean curvature flow rather than MBO. So you can see MBO actually wasn't the top performing. The modified mean curvature flow model actually worked even better, but it was also sort of inspired by some of the work that we've done with MBO. Okay, and then finally, I just want to mention that with my student, Xiang Luo and Andrew Stewart from Caltech and Kostas Sigalakis from Edinburgh, we've been doing some work on uncertainty quantification. I have some newer work on this, but this paper was sort of the one that started it all, where we look at this problem from a Bayesian statistical perspective for uncertainty. So if you're going to assign classes to data, you're probably going to have some pieces of your data where the classification is not so good, and others where it's quite good. And so you can try to assign an uncertainty score, right? So that And so you want to do it in a way that's well principled, right? That has some good mathematics behind it. And of course, the Bayesian statisticians have a whole corpus of work that's quite useful for that. And so, you know, this is just showing a picture of a result, right? So for example, with the MNIST data set, it's quite easy to see. So these are 4s and 9s, and you can see that the top row are the ones that have a low certainty score, their high uncertainty score. And then the bottom row are quite certain. And you can see that, especially with the 4s, like this one is probably not a 4, I would say. That looks like a 7 to me. And some of these 4s like that, these possibly could be 9s instead of 4s, right? And for those of you who are sort of new to MNIST and want to play with it, the 4s and the 9s are two of the most difficult groups to separate because they do have similar shapes. Okay, so that's some work that was published in SciMUQ in 2018. And I think I'll end here and just say that it's been really fun working with quite a lot of young people, and also some senior collaborators like Andrew Stewart and Yicheng Tai, who's now in Hong Kong. And you know, my colleagues in California, certainly Arjuna Flenner from the very beginning, who was in California when I started working with him, Alon Purkis, Mason Porter, who's moved to UCLA. So yeah, I'll just stop. And oh, and also I don't want to forget Christina Lorman at USC. We have a paper with her on modified Shiger ratio cuts using the Ginzburg-Landau model. So I'll stop there. And oh, I got to mention one more person, Alice Conegus. So the work that we did on the supercomputer was done with Alice Conegus, who was at Lawrence Berkeley Lab NERSC at the time we did that work. All right, I'm going to stop there. And thank you all for attending my talk.
Thank you, Andrea, for the very nice talk. So we have time for a few questions. We have...
Can Andrea hear you?
Andrea, can you?
Hi. I can't hear anything. I do not hear a thing.
Now?
Now I can hear.
Yeah, okay. So first of all, thank you very much for your very nice talk. So
The sound cut out again. But if people want to put a comment in the chat box, that would work.
yeah, now again.
Yeah, the sound completely cut off. Like once you said hello, I couldn't hear anything else.
Okay.
So maybe
Yeah.
put in the chat box.
Hi. Yeah, now. Yeah, sorry. So yeah, we have time for questions now. So maybe I can start with a question. First of all, again, thank you very much for your very nice talk. So I'm curious about the hyperspectral project. So I'm wondering, for instance, in the hyperspectral, when you're handling hyperspectral data, is sometimes when you're constructing the graph, is a computational trade-off between how many bands do you choose. If you do some dimensionality reductions before to construct the graph, and you take into account only relevant bands. So I'm wondering, how do you construct the graph? So you consider it all the full hyperspectral data, or did you do some dimensionality reductions and then you did this spatial spectral construction with the graph?
Great question. We used the full data set. We used all the spectral bands. We did not do dimension reduction on the bands themselves. So we didn't like start with a PCA or something like that, right? To try to reduce the dimension of the hyperspectral data set. No, in fact, this is the beauty of this method, is you can take very high dimensional data and you can almost make the dimensionality disappear by putting it on a graph. Of course, the expense is that in theory, you need to do n-squared operations, right, to do pairwise comparisons. But we don't do that, right? We actually can reduce it to an order close to an order n calculation by using either one of two approximations for the graph Laplacian, either a low rank approximation or a sparse approximation of the graph Laplacian. So we absolutely do not, and in fact, that's a really important point, we do not do dimension reduction of the hyperspectral data before putting it into the graph setting.
Okay, thank you.
Yeah, we often use spectral angle, right? We often do the spectral angle with these high dimensional vectors because, you know, for hyperspectral data, you can have, you're looking more at the shape, right? Mm-hmm. You can have two pixels that are very different in magnitude, but they have the same shape and they're describing the same kind of material. Like they could both be the same kind of grass. It's just that one is brighter than the other.
Yeah, that sounds great. Thank you.
Yeah.
So, do we have more questions in Zoom or here? Maybe another quick question is about the semi-supervised approach, the first approach that you discussed at the beginning. You show like a MNIST data set. I'm wondering if you try other more complex data set, like for instance, CFAR, and how the graph scale to that complex data.
Yeah, really good question. We have some work that's going to come out. You know, this is like a preview, right? We have some work that should be coming out in the next few months, and we have been trying these methods on, you know, on more complex data sets. We're kind of combining them with some, you know, neural network models, right? So the neural network can be used to generate graph weights in a very suitable way, like variational autoencoder is one way of doing that. That's an unsupervised way of generating graph weights. You can also use some supervision if you have some training data. So there's sort of a neat way to combine these ideas with some modern machine learning approaches. Let me just kind of point out that the methods that I'm presenting here are really meant ideally for problems with zero training data or very small amounts of training data. Whereas, you know, a lot of the neural network methods perform well if they have training data. So what's interesting is to try to combine the two approaches in a way that will sort of share the best of both worlds. And so we have some work that we're writing up right now that I hope to be able to share with you. Let me also mention that you know, there are some people who have been looking at kind of similar approaches as well. Yeah, I don't want to get too much into that because I don't have time today, but I'll just say that I think this is an interesting area of research. I'm working on it. One of the things that we've been looking at most recently is SAR data, synthetic aperture radar data, which is quite interesting, and there's not that much done from a machine learning perspective on that type of data.
Okay, that sounds wonderful. Thank you.
Yeah, thanks. Yeah, so stay tuned.
Hi, Andrea. I also have a question.
Yeah.
So first of all, yeah, thanks a lot for your talk. It was really great. I think it was a great finishing talk for the meeting. It was really quite fascinating. I think I probably have asked you this before. Sorry, let me just take off the mask. So yeah, that's better. I probably have asked you this before, but I wonder whether the answer has changed. So what about higher order derivatives on graphs? You know, like.
Yeah, good question. I mean, sure, like the same thing shows up. I mean, you and I have done some work on this, right? In Euclidean
Yes.
for in painting and so forth. Yeah, that's kind of a good question. It's not something that we have really looked at. I do not see that as an area where there's a lot of gains to be had from the data.
Okay. Yeah.
I think the discreteness, I think we're already stretching things, which is kind of funny because I often describe this as a rubber band approach where you stretch the rubber band around the data. But I think we're sort of, you know, we've stretched a little bit already the connection between the Euclidean curve shortening problem and the discrete graph problem. And I don't know that going to higher derivatives is something that is going to be that fruitful. That's just, and I say that with just purely with just kind of a gut feeling rather than having done any serious work in that direction.
Yeah. Okay. No, but that's really interesting. Yeah. Thanks a lot.
Yeah, sure.
Yeah, I'm just looking around whether there are more questions. Otherwise, I think Matea and I might go to the front now. And are there more questions online? No. Tatjana? No? Okay, well, Andrea, thank you so much for a really, really great talk. Let's thank Andrea again.
Thank you. It was a pleasure to see everyone. Sorry I couldn't come in person. I would have really loved to have made the trip over the ocean to Cambridge. And I hope that I can get there in the future at some point, but hopefully without a mask, but we'll sort of take this one day at a time, right?
Yes, exactly. So fingers very much crossed. Yeah.
Okay, great. Okay, bye-bye, everybody.
Bye. Thank you, Andrea.
Thank you. Thank you so much. Bye.
And then also thanks a lot to, I think, all the speakers, to all the participants for really great 2 days. We enjoyed it a lot.
It's very inspiring. Thank you for all the speakers, really fascinating talks, and everybody online and here in the room. And I'd like to particularly thank you, Carola, because you've done so much to put this to realize this workshop. So thank you very much, because it brought excellent people together, and I hope that it was inspiring to you as well. So yeah, thank you.